So we're back on this slide for cumulative frequencies. You can see this definition again. Your cumulative frequency is your number or percent of observations equal to or less than some value. And in that example we just looked at in the document camera, we did the number of observations equal to or less than some value, but you could do the same thing with a percentage if you wanted to. It would work out the same way. Note also here that we can only calculate cumulative frequencies for ordinal, interval, and ratio level variables. The reason for this is that we're looking at the number of observations that are equal to or less than some value. And in order to have less than be a concept that makes any sense, we need to be able to put our observations in order from least to most. So it wouldn't make sense to have a cumulative frequency for a variable like race, for instance, like in the activity example, because you couldn't say that you were coming up with frequencies for a race or ethnicity that was equal to or less than any other race or ethnicity. Just wouldn't make sense. So we're using our cumulative frequencies here for ordinal, interval, and ratio level variables only. And here's what some of these look like. So this is our ordinal level variable from the class data. Feelings about math. We've got a clear order from least amount of hatred of math to most amount of hatred of math, ordered in this way. And so looking at our cumulative frequencies in those parentheses there, we can see that in this class, 19 out of the 70 people have a level of hatred of math that is at it's okay or less hateful than that. 47 out of the 70 have a level of hatred of math that is not quite at the point where you'd like to gouge your eyes out. And then everybody hates it that much or less. Cumulative frequencies are sometimes useful for ordinal level variables. Sometimes they can muddy the water a little bit if it is something that you really have to think about, what less than or greater than means in a particular context. But you can calculate them and you would show them like this. They tend to be more useful when you're looking at data where you have numerical information, so interval and ratio level variables, with an example being this ratio level variable of police stops in the past 3 years. So here we could say how many people were stopped 1 or fewer times. We don't have to calculate anything. We can check the cumulative frequency and say that 42 people across the 2 classes were stopped 1 or fewer times. How many people were stopped 5 or fewer times by the police? Well, that's 63 out of the total class. And again, with all of these frequency tables, our goal is to take our information and organize it in a way that you get a picture of what's going on at a glance. And the cumulative frequencies can be helpful when you're trying to understand something like that. So, how often does something or something less than that occur? There is one more thing you can do with frequency tables that I'll talk about in this class, and that is grouping frequencies. So our mission remains the same. We are organizing our data into a way that you can get useful information at a glance. And group frequencies do this by grouping observations into ranges of values. This is a type of frequency table that only applies for interval and ratio data, so you have to have numerical data to create a group frequency table. And a group frequency table is more or less what it sounds like. So this is the original frequency table for the police stop data that was on the last couple of slides. And this is an example of a grouped frequency table using the same data. So what I've done here is I have grouped our observations into ranges. So instead of listing out each of the specific numbers that people put into the box, I have ranges now, 0 to 4, 5 to 9, 10 to 14. And what I did is I collapsed the information from the original frequency table into these ranges. So 60 people had been stopped between 0 and 4 times. 7 people had been stopped between 5 and 9 times. 1 person had been stopped between 10 and 14 times. 1 person had been stopped between 20 and 24 times, and 1 person had been stopped between 30 and 34 times. And so the usefulness of a group frequency table is that it can take a very long list of numbers and collapse it into a format that's a little bit easier to read. The downside to using a group frequency table is that you lose some detail. And I think you could argue that there's a qualitative sort of quality of life difference between being stopped by the police 4 times in a 3-year span and 0 times. But as you can see in our group frequency table, we're not distinguishing between those 2 things. And so that's the trade-off with group frequency tables. You're losing some information. Where they tend to really come in handy is when you have a whole lot of different possible observations for a variable. So this is also data from the class where I asked you guys how long is a one-way commute in minutes, And this is the information that, that I got. And what you can see here is that we now have a whole bunch of different observations, and we have a whole bunch of different frequencies. And we start to have the same problem that we did when we were looking at the original Excel spreadsheet, which is that it's just a lot of information. It's a lot of numbers. And to really make sense of what's going on in this data, you have to take the time to parse the numbers and think about where the large frequencies are and what the distribution might look like. You might have to picture it in your head a little bit. You know, where would this lump be if you made a graph? More on graphs later. But for the most part, that's not a quality that you want in a frequency table. You don't want people to have to stop and study it for a long time to figure out what it's saying. So we can turn it into a group frequency table instead to get around that issue. And what we can see here is that when we group our commutes into ranges, it's easier to read the table. And so we can now see that the most common commute length is between about 20 and 29 minutes, with 19 out of the 68 people who answered the question answering that question. 10 to 19 minutes and 30 to 39 minutes and 40 to 49 minutes are also pretty common commute lengths, and we've got similar numbers of people with each of those commutes. Relatively fewer are in the 0 to 9 range, and then relatively fewer people have commutes that are much longer than about 50 minutes. So group frequency tables, again, they cost you some detail, but they can be useful in organizing data that has a lot of different possible categories to it. You can also make some decisions in creating a group frequency table about what size you want your groups to be. The official technical term for these are bins, so how big do you want the bin in which you put your responses? And we can see this is the same exact data as in the original commute frequency table, but it's just collapsed down a little bit more. And so we're still going to be thinking about the same trade-offs. You know, how much readability are you getting versus how much detail are you losing? And so if you're ever creating frequency tables for any reason, your number one thought should be, you know, how well am I communicating this information? And you can think about things like how much detail you want to keep versus how difficult it is to make sense of the table if you have too much detail in there. And then one final note about these group frequency tables, they really come in handy when you have many, many, many more possible observations than this. So for some observations, you might have 1,000 different responses to the same variable. And you wouldn't want to list out all 1,000 observations with a frequency because that would be impossible to read. And that's where group frequency tables really come into their own. We just don't have a ton of examples of those variables in the class survey. So this is what I used here to illustrate that point. And that's frequency tables. So as part of this week's activity, I'll be asking you to make a frequency table. And so we'll come back to how to do that using software later on in the lecture. And for now, we're going to head into our second topic, which is visualizing data using charts and graphs. So this week's lecture is titled Organizing and Visualizing Data. We have now organized data, or we have already organized data, and we will now visualize data. And visualizing data generally refers to the use of charts or graphs. There are many, many types of charts and graphs out there. I'll be focusing in this class on a couple of commonly used ones. And each of these graphs that we're going to talk about does something slightly different with the data. I have listed here the ones we're going to talk about in this class. So we have line graphs, which tell you about frequencies over time. We have pie charts that tell you about frequencies for nominal level variables. We have bar charts that tell you about frequencies for nominal or ordinal level variables. And we have histograms, which are charts that give you frequencies for interval or ratio level variables. Histograms, as you can see by this little note, are going to be the one that will come back to haunt us most throughout the semester. So we'll briefly cover line graphs, pie charts, and bar charts here. They're good to know. They're good to know how to make. But we'll spend some extra time on histograms because they will continue to be relevant throughout the class, whereas the others will meet today, and then aside from the data analysis project, we won't be seeing them again. So graphing frequencies over time. if you want to show change over time, a line graph is probably going to be your best bet. And what a line graph shows are two axes. Your x-axis, or your horizontal axis, typically has some measure of the passage of time, and your y-axis, or vertical axis, typically has some sort of count or frequency, or could be relative frequency as well. So here's a silly one, but we have our passage of time as measured by year on the x-axis. We have the number of harpoons in space measured on the y-axis, and you can see we have a line showing over time how has the number of harpoons in space changed. And the line shows that continuity over time. We're tracking one thing, and we're seeing what it does. An actual line graph that's not just a cartoon here is this graph showing support for legalizing marijuana. It cuts off in 2018, but it's been more or less a similar trend since then. And what we can see is that we again have our passage of time as measured on our x-axis using year, and on our y-axis we have a type of frequency, in this case a relative frequency, so the percentage of people in the United States who believe that marijuana should be legal. And I always find this graph interesting because we think of the 60s and 70s as being, hippie times when everybody was just smoking weed and having a good time. But you can see from graphs like this that really support for use of marijuana was extremely low, and as low as it was in this entire period in 1970, and we've only become more accepting of marijuana use as a country since then, which we're now seeing in all of this legislation that's legalizing it in lots of different places. But that's a line graph. Another kind of silly line graph here is one that shows a different measure of the passage of time on our x-axis. So here, instead of measuring calendar year, we're looking at the passage of time as a child's age, where we're tracking the amount of dinosaur knowledge over time. And as a quick note here, my son is just turned 6, and I'm still waiting for him to hit a dinosaur phase, and I'm really disappointed that he hasn't yet because I am so hyped up to learn about dinosaurs, but we'll see. There's still time. All right, so those were some examples that I ripped from the internet. Here's an example of a line graph using the class data. And I've been teaching versions of this course since the spring of 2016, with some gaps in there, as you can see. And I've been giving versions of the course survey in each of those classes. One question that has made it onto every survey so far is that one about whether you would rather kill someone and have no one know, or kill no one but have everyone think you did. And this is a line graph that shows the percentage of students in the survey, so our relative frequency, who said that they would rather kill someone and have no one know, than kill no one but have everyone think they did. And what you can see here is that this line has been ever so slightly trending up since I started teaching. I don't think it means anything, but it's kind of funny to think about. But you can see we have these qualities of the line graphs that I talked about before, where we're measuring the passage of time on the x-axis, in this case by semester, and we're measuring a frequency on the y-axis, and we're seeing how that frequency has changed over time. The next kind of couple of graphs I'm going to talk about are graphs for frequencies for nominal and ordinal level variables. And I'll start with a pie chart, then I'll talk about the bar graph. And each of these graphs tells us more or less the same information. Pie charts are circular charts showing percentages, so relative frequencies as pie slices, and bar charts use the heights of bars to represent frequency or intensity of different kinds. Most people come into this class having seen pie charts or bar charts before. You typically meet them in middle school, high school, you just see them around. But we're still going to take the time to look at them to make sure that we are familiar with these ways of communicating data about nominal and ordinal frequencies. So here's the silly pie chart. It is the most literal pie chart that you could have. So we have a circular graph in which the slices add up to 100%, and it is literally pie I have not yet eaten and pie I have eaten as displayed in this chart. An example of a bar chart that I also stole from the internet, and that is also kind of ridiculous, is this superhero battle winner log. So I have no idea what the context is, but either way we have the characteristics of a bar chart here. So our variable would be superhero. We have different superheroes here: Batman, Captain America, Iron Man, and Superman. and we have a frequency for each of them. So we've got counts of winners in the superhero battle, whatever that was, where Batman has our highest win count and Superman had our lowest win count. And those of you who are comic book fans may have some questions, but we'll just leave it at that. Bar charts, as I mentioned, can also represent the intensity of things rather than frequency. So an example of that would be this graph about things I want to do in New Jersey, where there are various places you could go, and instead of counting something and showing that on the y-axis, we are showing intensity, so ranging from no to worse things to could be a good idea to I would do anything to do this. And the maker of this graph would really like to leave New Jersey. Personally, I've been in New Jersey for 5 years now, and I think it grows on me a little bit more each year. And I would no longer be in that leave category. I'm also going to show you some pie and bar charts from the class data. So these are not stolen from the internet and a little bit more serious, a little bit more like what you might want to present if you were asked to create a chart of some kind to present data. And you might remember from the class survey that I asked you some questions about how much money it would take you to do various things. These questions are borrowed from moral psychology research, in which they're used to gauge people's sense of morality in different domains. So how much do you have moral feelings about causing harm, including emotional harm? How much do you have moral feelings about doing things that might feel impure or gross? How much do you have moral feelings about things that might violate ideas about loyalty to your group or your country? And so I asked you guys, how much money would it take for you to insult a stranger? How much money would it take for you to wear a sweater that somebody had been murdered in, provided it had been cleaned since the murder? And how much money would it take for you to burn a flag? I also gave everybody an option to say that I would not do this thing for any amount of money. No, make me Jeff Bezos rich, I don't care, I'm not going to do this thing. And this is what the breakdown looked like for the class. So 40% of the class said that they would not be willing to insult a stranger for any amount of money. And 60% said, give me some amount of money, you typed it in, whatever it was, and I will walk out there on the street and call somebody a name to make that money. For the murder sweater question, we had slightly more people who said they'd be willing to do this for some amount of money, but 34%, so a little more than 1 in 3, still said that they would not be willing to do this thing for any amount of money. And similar breakdown for the burn a flag question, where 61% of the class said that they would be willing to burn an American flag for some amount of money, and 39% said that they would be completely unwilling to do this. So these pie charts show us the percentage of each response, again, as a slice of this pie in a circular graph. So I'm showing you pie charts because pie charts are just common sorts of charts, but they're really not all that useful for most statistical purposes. They're a little bit hard to read, they're a little bit hard to compare across, and so typically what you'll see when you're thinking about the frequencies for nominal level variables are bar graphs. And bar graphs are easier to read, easier to compare, easier to add things onto. And so I'm going to show you now the bar graphs for those same exact questions. Would you be willing to insult a stranger for some amount of money or not? Same answers here. You can see we have a little more than 40 said that they would be willing, a little bit less than 30 said that they would be unwilling. You could also show percentages on the y-axis if you wanted. Would you be willing to wear the murder sweater? Somewhere between 40 and 50 said they'd be willing, a little over 20 said they'd be unwilling. Would you burn a flag? Again, very, very similar distribution for all of these. In some semesters, these are all wildly different, but this semester we've got a pretty similar breakdown for all of these between being willing to do these things that violate people's sense of morality sometimes, and sometimes don't, right? Where you'd be willing to do it, no problem. As I mentioned on the earlier slide, we can also create bar graphs for ordinal level data, and here's some examples of what that might look like. One of the questions I asked on the slide was how you identify politically. Another question I asked was how often do you listen to country music? And so we can see on these bar graphs, we have a slightly different format, just to demonstrate some of the different formats you can do for bar graphs. We've got our different variable categories on the x-axis there, so that different values the variable can take on, and we have frequencies on the y-axis. Just as before, I could also have shown this with percentages if I had wanted to. These are the counts though. And what we can see is that across the two classes, the most common response by far was moderate for the political question, so 34 out of people out of the 70 or so who took the survey consider themselves politically moderate, and we have relatively more people on the liberal side, but mostly symmetrical graph on that one. How often do you listen to country music? People in these two classes do not listen to a ton of country music. 30 people say absolutely never, 17 people say once a month or less, and then we have relatively fewer people as we get to increases in country music. And this is a question that I throw on the survey sometimes, only because I only recently discovered that I like country music, and I was a snob about it for most of my life until a couple years ago, and then I realized that I actually like some of it, and now I'm just interested in whether anybody else has had that realization. So that's what we have for our bar graphs. So our final type of graph that we're going to look here in this class is going to be the graph that we can use for the frequencies for interval and ratio level variables. Where interval and ratio level variables, as you can recall, are numerical variables. Where we're measuring things, we're counting them in numbers, we have those same distances between each of our categories, whether or not we have a true 0 point. And the type of graph that we use to reflect these frequencies is called a histogram. And a histogram is a graph where the heights of bars represent our frequencies, similar to what we have in a bar graph. The main difference between a histogram and a bar graph is that in a histogram, everything is smushed together. In a bar graph, we have spaces between our categories that are meant to reflect the idea that there's not necessarily any continuity between those categories. They are distinct things, we don't know how far apart they are, so we're going to separate our bars. On a histogram, though, we have numerical variables. And there's not really a meaningful difference between, say, 1939 and 1940, if you're thinking about the year that A Christmas Song was released, and so we smush those numbers together on our x-axis. And we smush our bars together as well. But otherwise, what we're doing is we're creating these ranges of numbers, and we're showing the frequency of observations that occur in each range. And so this one is another XKCD comic graph, and it just shows that, at least when the graph was made, the most common Christmas songs played were songs from the 1950s, and with relatively fewer from other years. Another example of a histogram stolen from the internet is this graph of the caloric content in Chipotle meals. So somebody, for some reason, went through and calculated all of the different possible combinations of Chipotle ingredients that you could put together, and also calculated the caloric content for each one. And this is displayed in a histogram as well. So we can see these qualities of the histogram. On our x-axis, we have the values of this variable, the variable in this case being caloric content of Chipotle meals. And on the y-axis, we have a frequency. On this particular graph, if you can see, the font is a little bit small. This is a relative frequency, so it's the percentage of meals that have this each range of caloric content. And all our bars are smushed together to represent the idea that as you increase, by 1 calorie to another calorie to another calorie, we have continuity along that x-axis. We don't have entirely separate categories of things. We're on the same number line for all of them. And what you can see in that graph is that our most common caloric content for Chipotle meals is about 1,000, and there are relatively fewer meals that have a lot less than that, relatively fewer meals that have a lot more than that. I'm also going to show you some histograms for the class data. And as I mentioned before, histograms are going to be the type of graph that we'll see a lot throughout this semester, so I'm going to spend a little bit more time talking about these histograms and ways we can describe them than I did the other graphs also. One question on the class survey was, how tall are you in inches? here is a histogram representing that data. So we can see that in the two classes, the most common heights are around 65 inches, so about 5'5". Relatively few people are much shorter than 5'5". Relatively few people are much taller than 5'5". And the histogram displays that in this format, where we have our variable values on the x-axis, our frequencies on the y-axis, and all of our bars smushed together to show that continuity. Another question I asked you in the class survey is, how certain are you that you'll get an A in this class? And we can see our responses here, where we've got values ranging from 0 to 100. The most common answers were relatively high certainties, which is always nice to see. So most people were, somewhere between 90 and 100% certain, or 80 and 90% certain that they do well in the class. And then we have relatively fewer people who came into the class feeling less certain. I also asked you, what's the greatest number of drinks you've ever had in one night? So on your wildest night of partying, what did you get up to? And we can see the opposite pattern in this graph as we have in the A in the class graph, where we've got between 0 and 5 drinks being a very common response, between about 5 and 10 drinks being a very common response, and relatively few people having had many more drinks than that. And so we've got these same histogram qualities here. We have our drinks on the x-axis, frequency on the y-axis, and bars all pushed together to show the continuity between each increase in a single number of drinks from one to the next category. In addition to describing the shape of the histogram informally like I did on the last slide, we can also formally describe how a distribution is shaped, where we're literally describing the shape that we see in front of us looking at it. And one of the ways that we can do this is by talking about whether or not that distribution is skewed. So some distributions we can describe as symmetrical, where a symmetrical distribution is what it sounds like. It's more or less the same on either side. So typically in a symmetrical distribution, we're looking at most of our data, most of our responses being somewhere in the middle of the distribution, with relatively fewer observations that are a lot smaller and relatively fewer observations that are a lot larger. And it doesn't have to be perfect exactly, especially when we have a relatively small sample like a 70-person class sample. You're just bound to get some bumpiness. But what we can see here in this height graph is that we have that pattern. So our most common observations are towards the center of the distribution, and then we have relatively fewer people who are much shorter than our center, and relatively few people who are much taller than our center. So we could consider that symmetrical. We might also have a distribution that is what we call left skewed. And an example of left skewed distribution is our confidence in getting an A in the class variable, where a left skewed distribution is somewhat counterintuitively one in which most of our responses are on the right-hand or more positive side of the graph, and we have relatively fewer responses trailing off towards the left. And I like to think of it as being kind of like there's an arrow pointing out towards the left. So we could say that for our left skewed distribution here, we've got this shape where we've got an arrow pointing out towards the left. And we would call that left skewed. A right skewed graph is exactly the opposite, where for a right skewed graph, we have most of our responses on the left-hand side of the graph, and relatively fewer responses trailing out towards the right. So if we were to draw a line over it, we could say that for a right skewed graph, we have this long tail or long arrow here pointing out towards the right. And the formal statistical term for that is actually a tail. So you might hear me say that again. And then, again, coming back to this symmetrical graph, we can say that we have a shape that is more or less symmetrical. We don't really clearly have a tail going in either direction. We've got them kind of pointing out on both sides away from the center. So again, we can describe our histograms or our distributions in terms of shape, or you could have a symmetrical one, where it's more or less the same on either side. Bulk of your data is in the center of that graph. You could have a left skewed distribution where most of your observations are on the right hand or more positive side of the graph, and you have that tail pointing out towards the left. Or you could have a right-skewed distribution where most of your observations are on the left-hand side of the graph or more negative side of the graph, with that long tail pointing out towards the right or towards a more positive direction. So that's one of the ways that we can describe shape. There are a couple of other ways as well. Some distributions are what we call bimodal or multimodal. And a bimodal graph is a graph that has two distinct humps to it. So this one is borrowed from the internet. This isn't real data on test scores from any students I've ever had. But what this shows is a hypothetical distribution for students who both did study for a test and didn't study for a test. And you can imagine this happening if, some students study really hard, but some get luckier, have a better day than others, and have higher test scores. So we end up with our first distribution on the right there. And then you have students who didn't study for the test. Some of them also had better days than others, but they're also having lower scores in general because whatever base analogy need they don't have. We would call this a bimodal distribution because we have these two distinct humps. A multimodal distribution would be one that had 3 or more humps to it. I'll note that here, but we won't be talking too much about bimodal or multimodal distributions for the rest of the class, so I will leave us at this for bimodal distributions. One other characteristic of distributions that we can describe in terms of shape is called kurtosis. And the kurtosis of a distribution describes how tall and skinny it is or how wide and flat it is. And we have these words here for describing those distributions, leptokurtic, mesokurtic, and platykurtic. I am introducing them on this slide to let you know that they exist. As you take other classes, especially if you continue on with statistics in your careers, you'll likely see them again. But for the purposes of our class, we're going to leave it more or less at this slide here and say that these are the names for these types of distributions. When we see them later on, I will most likely just refer to them as tall and narrow or wide and flat. But this is the official set of terms for describing distributions in this way. All right, so to round out our discussion of graphs and charts here, I also want to talk a little bit about one of those statistical problems that you should always be on the lookout for, and that problem is misleading graphs and visualizations. And this is a chart that I came across online when I was looking for the fun examples to populate those earlier slides. And every time I look at it, my blood pressure goes up a little bit because it's one of the worst charts that I have ever seen out there in the wild. And the reason for this is that in creating a chart, your number one goal should be to communicate information effectively. And a graph like this does not do that. And instead, it would lead you to come away with the exact wrong idea if you just took it at a glance and then left. And what's wrong with this graph is that we're showing these percentages, whatever they're percentages of, using wine glasses that are some amount full. But the percentage of the wine glass that's full does not match up with the percentage that's shown above it. So if you were just glancing at this picture and you saw that one on the left side that's all the way full versus the one on the far right that's not at all full, your brain would take that picture and think, well, that's got to be close to 100% on the left, and that's got to be close to 0% on the right. But the actual numbers that they show don't match up with that at all. And so it exaggerates the distance between them because you're visually showing something different than what the actual percentage is. So if I were to make this graph, if it had to be wine glasses, I would want that leftmost wine glass to be 24% full, not maybe 90% full like what it actually is. So the very last thing that we will look at today is how to create frequency tables and different types of graphs and charts using software. Because it's extremely unlikely that you'll ever be in a position where you would need to do it by hand like I did in the earlier examples. And specifically, we'll be using Stata to create both frequency tables and graphs and charts. So first, I'll talk a little bit about frequency tables and histograms, and I'll talk about the other charts. So to create a frequency table for any variable in Stata, your first step is going to be to open your data file. As a reminder, you'll need to do this on the Rutgers Virtual Computer Lab. So that's what hopefully you were able to do last week. If not, if you have any issues or questions, or if any new issues or questions pop up this week, please feel free to reach out. I'm always happy to troubleshoot technology issues. Once your data file is open, you'll see a command box, which will be a place where you can type things in. To get a frequency table, you're going to type in this blue command here, so the word tab followed by the variable name, and then press enter. To create a histogram for any variable, you can follow a similar process. So first step, open your data file. If it's already open, you don't need to do this step again. And then type into that command box this blue text here. So histogram followed by your variable name, followed by this comma, and then frequency. Press enter, you'll get a histogram. It'll pop up in a new window. For histograms, you can also use the menu at the top, and I'm going to demonstrate all of this at the end of the lecture as well. You can also use the menu, select graphics, and then histogram, and it'll give you a place to type in the variable name and select some other options as well. So I'll also show you how to do it that way. You can also create pie charts and bar charts in Stata. So for both of these, you'll need to open your data file first. Again, if it's already open, you don't need to open it again. And then you can type more commands into this command box. To create a pie chart, you can type in this command in blue here. To create a bar chart, you can type in this command in blue here, and I'll demonstrate both of those as well. To create these types of charts, you can also go into the menu bar, and it'll give you some more options as well. So I'll show you how to do those. So I'm going through relatively quickly on these slides because I'm going to demonstrate step by step in the next video. This is here mostly so that you have a reference for the syntax and have it all on a slide, so you don't actually need to watch the video every time to see it. Before I do that, though, I'll also talk through our third activity. So your mission for this week is going to be to create your own frequency table and graph and describe one of the variables in the class data. So what I want you to do is to pick some variable from the class data that was not already used in this lecture. So if you already saw a frequency table or a graph for a variable in the data, don't use it for your activity this week. Still leaves plenty of options that you could use. Then I will ask you to use Stata to create a frequency table for the variable you've selected, as well as a graph for that variable. As a reminder, you can create a frequency table for any kind of variable, but different types of variables require different types of graphs. So think about the level of measurement of the variable that you chose and make sure to select your graph accordingly. Then, after you've created those things, I want you to summarize what you've learned about that variable in one sentence. As an example, for that number of drinks variable that I showed you a histogram for, I could have written something like, the majority of students have had less than 10 drinks on their wildest night of partying, while relatively few students have had many more drinks. And so I'd be summarizing the story I learned from that variable that I'd be able to see in a frequency table or in a graph. And I would just be describing it as my main takeaway in a sentence there. So I'm going to be asking you to post your responses to Canvas by this Sunday. And again, the last thing I'm going to do before I end out this video lecture entirely will be a tutorial demonstration of how to actually get each of these things to appear in Stata. As a note, in order to do this activity, you will want to refer to the course survey codebook that has now been posted to Canvas. You can find it both in the Activity 3 discussion and also kind of free-floating in that course survey module. And this codebook I'll also show you in a minute, but it describes the variable name for each variable, so how it's listed in the dataset, as well as how each of those variables was coded. So you may need that to interpret your results in the frequency table or graph, so whatever you see. All right, and so with that, I will now head over into the tutorial, but as always, any questions about this activity, any issues, please do not hesitate to reach out to me.